Now that we know a little bit about exponential functions and their graphs, we are going to discuss in this video how to identify whether or not a function is an exponential function. And we're going to do it in 3 different representations. We're going to do it by looking at equations, by looking at tables, and by looking at verbal representations. So in the first example, we're going to look at equations. Now remember that exponential functions are in this form where we have x in the exponent. So if we look at this first one here, x is not in the exponent. This is not an exponential function. This one here is in the form a times b to the x, where x is in the exponent. So this is an exponential function. This is also an exponential function. The x is in the exponent, and there's been a shift of 5 horizontally to the left because we added in a 5 with the x, and it's been flipped over the y-axis because we put a negative in front of the x. So although this isn't in our standard form of being in the mother function form, this has been shifted. Okay, this one here, the x is not in the exponent, so this is not an exponential function. Now, when we look at tables to determine whether or not it could represent a linear or exponential model, the difference between linear and exponential is linear increases by a constant amount and has a rate of change that doesn't change. It's always the same. For exponential functions, this increases by a relative amount, which means by a percentage. So it's not going to be the same amount every time. It depends on the previous value. If I increase something by, say, half, that means I'm going to take half of it and add it to it. Well, depending on what that number is, it could be a really big number or it could be a really small number. For example, if I take half of 100, that's 50, and if I add it to it, my new value is going to be 150. Versus, so I went from 100 to 150, so that's a jump of 50. However, if I look at the number 4, and I take half of 4, that's 2, and I take 4 and add it to 2, that gives me a 6. So I jump from 4 to 6. That's only a jump of 2, even though I went and increased by 50%. One is a jump of 2, and the other is a jump of 50. So there's a big difference in increasing by a constant amount versus increasing by a percentage. So if we look at this first table, x is increasing by 1. So every time I increase by 1, notice what I'm increasing for y. Every time we keep adding 30 when we add 1 for x. So this is going to be linear because the change in y over the change in x is always going to be the same. It's going to be 30 over 1, 30 over 1. However, if you look at this second table, as I go up by 1, it's not increasing by the same amount. From 15 to 45, I would add 30. Then from 45 to 135, I'm not adding 30 again. So this is definitely not linear because I'm not going up by the same amount. However, if you notice, if I take 15 and I multiply it by 3 and I triple it, I get 45. Then from 45 to 135, I'm getting tripled again. And then again. So I'm increasing this by 300%. Okay? So this is by a relative amount because I'm multiplying. by the same value. Whereas over here, it's increasing by the same amount every time. So this one here is going to be exponential. Now the last example, when we look at our verbal representation, in the first example, it says the average annual population increase of a pack of wolves is 5. So every year it increases by 5. So when the year changes by 1, the number of wolves increases by 5. So this is a constant change. This is an increase by 5 every year. It's constant. So this is going to be an example of a linear function. Versus if you look at example B, it says after the antibiotic is ingested, the bacteria decreases by 50% every 6 hours. So this is changing by a relative amount. So it's going to depend on the past 6 hours how much it decreases by. You're going to take 50% off of that and then 50% off of that. It's not going to be the same amount every time. So this decreases by a relative amount. So this is exponential.